All right, let's jump into section 4.3 about this is going to be able to give us some more information on how to accurately graph a function, knowing derivatives and what gives us from those, what information is given to us from that. So this section will continue on the idea of critical numbers from section 1 and learn much more about the behavior of functions with some tests. So the first one that we get is increasing and decreasing. Obviously, if we're increasing, we're going up. If we're decreasing, we're going down. What that looks like in a function is if we're increasing left to right, decreasing, increasing, that type of stuff is what we're looking at for this. So suppose that f is defined on an interval I. We say that f is increasing, and these are the mathematical terms, but logically you should do what kind of I just did for us there on the left-hand side. We're increasing on I if f of x sub 2 is greater than f of x sub 1 whenever x sub 1 and x sub 2 are in the interval and x sub 2 is bigger than x sub 1. So basically, as I move to the right and get larger, then the function values get larger when we are increasing. And we say that f is decreasing on the interval I if f of x sub 2 is less than f of x sub 1 whenever x sub 1 and x sub 2 are in I, and again, x sub 2 is greater than x sub 1. So the function values are decreasing this time when our x's get bigger. So for a couple illustrations, increasing would be something like this, where maybe I let this be x sub 1 and this be x sub 2. So x sub 2 is bigger than x sub 1. Therefore, should be up here a little bit more. F of x sub 2 is bigger than f of x sub 1 when we are increasing on our function. And if I have some kind of decreasing function, say like this, call this x sub 1 and x sub 2. Again, x sub 2 is bigger, but here now, f of x sub 2 is smaller than f of x sub 1. So this is, in a sense, this is our decreasing version of that mathematical statement. Now, obviously, we want to be logical about all of this and know that when going left to right, if something is going up, it's increasing. If it's going down, then it's decreasing. So let's connect this to the derivative now. Recall that the derivative of a function gives the slope of the tangent lines. And if the derivative is positive on an interval, the tangent lines on that interval have positive slopes, and the function is increasing. But if the derivative is negative on an interval, that means that we have a negative slope on our tangent line and the function is decreasing. So if we kind of look at kind of those same graphs that we just somewhat looked at, if I have an increasing function that looks like this, and I try to envision all the tangent lines along here, all of these tangent lines have a slope that is positive. Tangent lines have positive slope, aka that's the first derivative. This is on an increasing function. But if we end up having a decreasing function, and I like to project the idea of my tangent lines, maybe I change my color here, my tangent lines along the way, each one of those have a slope that is negative. So, tangent lines have negative slope, and that is, remember, the derivative, and this is for a decreasing function. So, we have to have some kind of test for increasing and decreasing. Well, if I'm increasing, we have positive slopes. If we are decreasing, we have negative slopes of the tangent line. So here's our test. It says that suppose f is a continuous function on an interval I and differentiable at all interior points of I. So basically one of those open and closed intervals. if f prime of x is greater than 0, if the derivative at any x value is greater than 0, which is positive, at all interior points in I, then f is increasing on I, and if f prime of x is less than 0, aka negative, maybe we should put that here, positive, negative, then f is decreasing on I. So just given that information, could we construct a graph here just by knowing those pieces of information? Now, it's not going to be an accurate graph. It's just going to be kind of a sketch here. But sketch a graph of a function that is continuous on all real numbers and satisfies following conditions. So I'm going to look right here on this. I'm going to look right here on this. So I'm going to kind of make a number line. I like to go with some number lines here. And we're breaking at 0, 4, 6, 0, 4, so 0, 4, and 6. Now, the derivative is greater than 0. It is positive from negative infinity to 0. So remember, this is my graph of my f prime. What's happening on my derivatives? From 4 to 6, we're also positive, and from 6 to infinity, we're also positive. The only time that we're negative is if we are between 0 and 4. Now, we know that the derivative is undefined at 0, and the derivatives are 0 at 4 and 6. Now, let's break this apart before we start drawing, okay? Over here, if this is positive, we were just told on our test of increasing and decreasing that our function is increasing in this interval, increasing and increasing. Then our derivative here is negative, therefore our function is decreasing from 0 to 4. That's the only time it's decreasing. Now, I'm also told that at 0, our derivative is undefined, okay? F prime does not exist. It's undefined. So what kind of things on a graph allow us to not be having a derivative that's defined at a point? Well, there's a couple things that could happen. One thing, you could have an asymptote on your graph to where your derivative would not be undefined. But another place would be at one of those pointy points that I talk about, where it's a cusp or, a sharp turnaround point at that place. So at 0, we're going to draw a pointy point. At 4 and 6, because our derivatives are equal to 0, that means I have a nice smooth max or a min at 4 and 6. So we're going to have a horizontal tangent here at 4 and 6. Horizontal tangent. So putting all that information together, we should be able then to create a graph, okay? Now again, it's not a very accurate graph because this is all we know. Notice that we are increasing until we get to 0. And at 0, we have that undefined pointy point of that derivative. But then we have to start decreasing at that point. So I'm going to do, something like this. If I end up doing something like this, and then I do one of those cusps here, where I'm now going to decrease starting at 0, but I'm going to get to a point where I'm going to start increasing again at 4. Okay? So I'm going to decrease, and then at 4, I'm going to start increasing again. So at 0, we're going to decrease 1, 2, 3, 4, 5, 6. So let's put that out there. Then we're going to have a pointy point here at 0, so that I have an undefined, but I'm going to decrease until I get to 4. Now, at 4, we increase from here on out. The positive derivative tells us that we are going to increase, but what happens at 6, though, when we have to have a horizontal tangent? Well, if we're keeping on increasing, if we're decreasing and then increasing, that's going to be nice, and we have that horizontal tangent. But at 6, what happens is that we're going to create one of those cubics. If you recall, we had, in one of the sections, I believe 4.1, we talked about where we have a horizontal tangent on a cubic shape. And so I also have a horizontal tangent here. I have a pointy point at 0, where our function is undefined. And we have increasing, decreasing, and increasing the rest of the way. So I've satisfied every single condition that they gave me for this situation. Okay, so I like to see these number lines like this. This helps me kind of get myself kind of organized so that I know what to do from there. So let's look at this. Given a graph, can you determine an original graph? This is the derivative graph. can we then determine a sketch of an original function that satisfies all of these. So the following figure gives the graph of the derivative of a continuous function that passes through the origin. So that means when I do my graph, I'm going to have to be going through the origin. Sketch a possible graph of f on the same set of axes. Well, we're going to kind of do it on the side. Here, I'm going to extract out of here a one-dimensional number line so that I'm aware of where we are increasing, decreasing, because this gets me confused. If I kind of see this one-dimensional number line like this, then that kind of gets me in sync. So I'm going to locate where my zeros are for my f prime. And in this case, it's going to be at -3 and 1. That's where the changes are going to occur with my zeros. I need to evaluate where is that function to the left of -3. Well, it's positive. All these numbers are going to be positive. That means it represents positive slopes here. All of these guys between -3 and 1 are negative. All the slopes on my original function, this is just a graph of those, they have to all be negative. And from here on out, we're going to be positive. So what does f prime tell me? F prime tells me increasing and decreasing. This tells me since it's positive, it's increasing to the left of 3, then it's decreasing between -3 and 1, and it's increasing again from 1 to infinity. But the thing is I've got to go through the origin, okay? So let's put in -3 and 1, because those are kind of important spots. I'm going to increase till I get to -3, then I'm going to decrease till I get to 1, but I have to go through the origin. Okay, so I'm going to increase until I get to -3, but I'm going to decrease through the origin until I get to 1, and then I'm going to increase again. Therefore, that would be a sketch of my original function that I have. Okay, increase to -3, decrease till 1, but going through the origin, because it told me that, and then I'm going to increase again at that point. So here, this is just a very bare sketch of what we have to satisfy those. Okay? Now, that's given some graphs, but what if you're given a function? Can we then figure out where we're increasing and decreasing? Well, that's important because those things are going to occur at our critical points. So remember, those critical points are important pieces to our graph, in which we kind of incorporate some relative max and relative mins, or local max and local mins. So we have to make sure that we find those critical values where we're equal to 0. So this actually would be a critical point, and this is going to be a critical point because f prime equals 0 at those, okay? So let's first take the derivative of our function. Give me 4x cubed minus 12x squared plus an 8x. Excuse me. Then we're going to set that equal to 0, factor out anything that's in common, and in this case, I'm going to take a 4 and an x out. And when I do, I'm left with 4x minus, x squared minus 3x plus a 2 equal to 0. And I'm going to keep factoring. Hopefully I can factor. That's always the nicest. And in this case, I can. X minus 2 and an x minus 1 is the way that we factor. And so, what makes this 0? Go down the line is 0. What makes that 0 is 2. And what makes that 0 is 1. So at this point, what I want you to do is kind of just do a one-dimensional number line with these critical points on it, okay? So I'm going to put 0, 1, and 2. Now, this is the time where we have to assess the values of my derivative. So that means I need to check some regions here, okay? So remember, this is of f prime. So when I check these regions, I have to plug it in here or plug it in there, not the original. You do not put it in the original, you put it into the derivative. So I'm going to choose, say, -1. If I put -1 in each one of these factors, what happens? -1 times 4 is going to give me a negative answer. -1 minus 2 is a negative answer. -1 minus 1 is a negative answer. And I'm multiplying all of these together. So when I multiply 3 negatives, ultimately, I get a negative answer. So on this interval from -infinity to 0, the first derivative is negative, which means that we are decreasing on that interval. Now, here's where knowing some tricks of the trade will save you some time. Notice that none of these are double roots. Anytime you have an odd power on your root, a 1, a 3, a 5, whatever the case may be, the signs over those roots change. So if this is a negative, since I have a 1 here on that, then this would be a positive. Since I have a power of 1 on my root of 1, then they're going to change sign over 1. Since I have a power of 1 on my root of 2, then it's going to change sign. So that's going to alternate signs because we have 0 double roots. That's a way to save yourself some time when you are looking at some of these. Sometimes you just have to plug them in, but polynomials are nice. You can go through there and change those signs. But you could also then plug in 1/2, plug in 1.5, and plug in 3 and see what you get. Whenever you do that, you will yield, when you multiply those 3 factors, you will get positive, negative, positive for each of these sequential regions. So what does that mean? If our derivative is positive, that means that I'm increasing in this region. I'm decreasing since it's negative, and I'm increasing here. So the question said to find the intervals on which f is increasing and which f is decreasing. So for increasing, we would be from the positives, from 0 to 1, and we would be from 2 to infinity are our intervals of increasing. For decreasing, we would be from negative infinity to 0, and from 1 to 2. And that would be our final answer for that problem. Okay? All right, very good. Let's try this next one. Now, this next one's not necessarily a polynomial, but it is one in which we can take a derivative pretty nicely if I distribute that through. So I'm going to make an equivalent here of this function. When I have to add these exponents, this is like a 6/3 plus a 2/3 gives me x to the 8/3 minus x to the 2/3. And now we're going to get ready to rock and roll and take our derivative. So finding our critical points is important because that's where the action happens. So we're going to bring the 8/3 out front and decrease that power by 1, which is 3/3. So 8/3 minus 3/3 is 5/3. Minus, bring the 2/3 out front and decrease that power by 1. So when I, do that. So when I decrease that power by 1, I get 2/3 minus 3/3, which actually gives me a negative 1/3. So I get 2/3 x to the minus 1/3. Now, here's the chance that you need to factor things out. Now notice there's a 3 in the denominator that's in common, and in the top there's a 2. So I'm going to choose to factor out a 2/3. Sometimes those fractions can be kind of a little bit wonky. I'm also going to factor out the common x, but it is the lowest power here, which is x to the negative 1/3. So what is left over? Well, 2/3 times what is 8/3? Well, I need a 4 on top. Now, x to what power, when added to negative 1/3, gives me 5/3? So negative 1/3 plus what has to equal 5/3? That's what you need to do. When you add that over, you get 6/3, which is the same as 2. So I need x squared there, and that's where factoring some of the negatives out might be a little bit tricky, so you want to practice that. Then I took out 2/3 and x to the minus 1/3, which is nice because that's all of it. So I get minus 1. Now, where is that equal to 0? Well, first off, this is going to go in the bottom, and I'm going to have this on the top. So I can actually do 2 times, and I'm going to go ahead and factor that difference of squares right here. 2x minus 1 and a 2x plus 1. All over, bring the 3 in the bottom and the x to the 1/3. And those factors are in my derivative. Okay, now actually I shouldn't say equal to 0 on this one. There's equal to 0 and undefined. So there's going to be 2 places where we're equal to 0. The opposite of 1 over 2, the opposite of this over 2. So I get a 1/2 and a negative 1/2. And where is it undefined, do not exist, it's at 0. So there's kind of 3 critical points here. 1/2, negative 1/2, and 0. And those are the things that I want to put on my paper for my one-dimensional number line. Negative 1/2, 0, and 1/2. Okay? Now, here's the thing. You got to remember, plug in these values to your derivative or to your derivative. Being able to use your graphing calculator or your scientific calculator is really important here to making sure that you get the correct values. Now, on this one, there's no real trick. We want to make sure that we adhere to figuring out what values that I have inside here in that interval and plugging it into the derivative, so you can plug it here or you can plug it here, doesn't matter. But I'm going to save us some of that time here. And when I plug in, say, -1 into all of this, you're going to end up with a negative answer. If you choose like -1/4 and you plug it into all of these x values and you figure out what kind of answer that you get, you end up with a positive answer. Then when you plug in this region, you get negative, and in this region, you get positive. So that's some of the work that you have to do behind the scenes on that. Now, once we have that, we can go down the line and say, okay, these negatives mean that my function is decreasing at this time. These positives means that my function is increasing at this time. And so the increasing intervals are from -1/2 to 0 and from 1/2 to infinity. And my decreasing intervals are going to be from -infinity to -1/2 and from 0 to 1/2. So it's imperative that you remember if your derivative is positive, it's increasing. If your derivative is negative, your function is decreasing at that time. So those are going to be our final answers for that. Okay? All right, very good. So let's use the idea of increasing and decreasing to expand upon this to end up getting our local extrema. Okay, using what we know about increasing and decreasing, we can now identify local extrema, which is our max and our mins, and we're going to look at 3 different graphs. So one of them is going to be if I end up having a function that decreases, then increases. Okay, I'm going to call this some c value, call this over here a, call this b, or something like this. If I look here and I am a decreasing function, that means that my derivative is less than 0 here, if we're decreasing. We just talked about that. If our derivative is positive, that means our function is increasing, so that means that our derivative has to be positive here to the right of c. So f prime is negative, then it's positive. What do I create if I am decreasing, then increasing? Notice this guy right here is a minimum. If I have an increasing function, then a decreasing function, call this A, call this B, and at C, what do I have? I know that the derivative, if it's increasing, the derivative here has to be positive. And the derivative here, when I'm decreasing, has to be negative. And so therefore, if my derivative goes from an increasing to a decreasing part, what do we know about C? Well, that's one of those maximum values that I have. Now, the third graph doesn't really yield a max or a min, but it's the thing I want you to realize that if you have a consistently increasing function or a consistently decreasing function, let's kind of take that cubic, that x cubed little squiggle, and I around this point of C, call this part here A or B, and call this part A. Notice that if we are consistently increasing by our first derivative, that means that f prime is positive and f prime is positive around C as well. Now we'll talk about this little point right here in just a few minutes, but at this point there is no local max or local min at that point, okay? So make sure that you realize that it doesn't always have to be a max or a min. So assume that f is continuous on an interval that contains a critical point C, and assume that f is differentiable on an interval that contains C, except perhaps at C itself. So there's a case where it may not have to be defined at C. If f prime changes from a sign of a plus to a minus as x increases through C, so let's go from a plus to a minus as x increases through C, what do I know? Then f has a local max at C. There's a maximum. If f prime changes from a negative to a positive as x increases through C, changes from a negative to a positive, I'm decreasing, then I'm increasing. That means that we have a minimum value at C. And if f prime is positive on both sides near C, or negative on both sides near C, then f has no local extrema or extreme value at C. So that's the case that I have over here with this cubic in that case. So that is what we refer to as the first derivative test. And how can we use that? Well, that now identifies increasing, decreasing, local max, local min, no local max or no local min. And so we would be able to then get some more information about our graph. So we want to find the local absolute extrema of the function using the first derivative test. Now, the absolute extrema now brings in the fact that we have to evaluate the endpoints to see which is the biggest, which is the smallest, okay? So we first want to find our critical points. Always important just to find those critical points first by taking the derivative, setting that equal to 0. Notice everybody has a 6, so I'm going to divide everybody by 6 to get x squared plus x minus 2 equals 0. And I can factor as an x plus 2 and an x minus 1. So making sure you can factor, that's very, very, very important. All right, so the critical points that I have for this function are -2 and 1. Notice -2 is actually an endpoint, and 4 is also an endpoint. So I'm looking here at my graph of f prime. I'm going to go from -2 to 4. And I have 1 in between there that I have to assess. Okay, now what happens on the behavior around 1 for the first derivative? So if I choose a number between -2 and 1, say 0, I always like to choose 0. Put 0 in here, I get positive, 0 in here, I get negative, so a negative times a positive is a negative. There are no double roots, so I'm guaranteed them to alternate over that root. If you want to try to plug in 3, plug in 3. 3 is positive here, 3 is positive here. Ultimately, it's positive, so it works. So what do I know about my function here? Whoops, I don't want to say increasing, I want to say decreasing because it's negative. And I'm increasing here from 1 to 4. Now, what does that constitute from our first derivative test? Our first derivative test says that it goes from a negative to a positive, then f is a local min. We are decreasing. I always like to think of it decreasing and then increasing. I have a minimum at this. So we know we have a local min at 1, but what is the absolute max and what is the absolute min? And when I throw in this absolute, now I have to check the endpoint. So I have f of -2. Let's look at f of 1 and f of 4. Now, these are the actual function values. So to find these, we've got to put it back up into here. And again, having your calculator help you out is important for time purposes. I'm going to tell you that I end up with all of these, okay? So 21 when you plug in -2, -6 when you plug in 1, and 129 when you plug in 4. So what does that mean? When we ask for the local min and local max and the absolute max and the absolute min, we know that this is going to be a minimum already, but here this constitutes for the interval an absolute min actually. It's actually absolute and a local min, if you ask me. They're the same kind of. And here, a maximum, this would be, there's no local max within here, but there is an absolute max on the interval of 129 when x equals 4. So that would be our conclusion for each one of those. Oops. Okay. All right, let's try the next one. The next one is, again, another function that I'm going to choose to distribute that through so that I can take the derivative with the power rule. So g of x is equal to, let's go 2x to the 2/3, and then minus, when we do 3/3 plus 2/3, I get minus x to the 5/3. So let's take the derivative of that function to yield any critical points that we need. So I'm going to bring the 2/3 out front, times it by 2 gives me a 4/3. Decrease that power by 1 gives me a negative 1/3. Minus, bring the 5/3 out front. Decrease that power by 3/3, which is 1, gives me an x to the 2/3. Okay? If I were you, I would take out a third. I would also take out an x. So if I take out 1/3, I'm going to take out an x, take the lowest power, which would be a negative 1/3. And what am I left over? Well, I took this completely. I took a third. I'm leaving the 4 minus. I take out the 1/3, so I'm leaving the 5. And x to what power when added to negative 1/3 gives me 2/3. So Negative 1/3 plus what equals 2/3. If you solve that equation, add the 1/3 over, you get 3/3, so it should be x to the first power. So I will write it like that. Now, what are our critical points? Critical points here are what makes this 0, and this would make it undefined for your derivative. So the critical points here are, well, if we solve this for 0, set that equal to 0, add over to 5x divided by 5, you get a critical point of 4/5. And what makes this undefined, because this would be a negative in the denominator, would be x equaling 0. So along our one-dimensional number line, whoops, let's go G prime, not F prime, since we're in G this time. Then we want to put 0 and 4/5 on our line. But we also have to look at negative 1 and 2 to include the absolutes, okay? So where's our local max and min? Where is going to be some absolute max and mins? So let's first talk about the local max and mins. I need to determine, are these plus or minuses up here? So again, choose a number like negative 1/2, plug it into the derivative, here or here, doesn't matter. I will tell you, you will yield out a negative answer there. If you put in, say, 1/2, 1/2 is between 0 and 4/5, put in 1/2. I don't care what the answer is, I just care about the sign. It is positive. And if I plug in, say, 1, plug in 1 to there, you will end up with a negative answer as well. So what happens? From a negative to a positive, I'm decreasing, then increasing. That makes this a local min. Then I'm increasing, then decreasing. That makes this a local max, okay? So local min at x equaling 0, a local max at x equaling 4/5. That's a conclusion that we can make just from the derivative. Now, to determine the absolute max or absolute min, that means that I have to evaluate g of negative 1 and g of 2, which are the endpoints, and g of 0 and g of 4/5, which is our critical points. So we're kind of bringing in stuff here from section 1 along with section 3 to determine out these maxes and mins. So I'm, again, plug this into the original. Put it in your calculator and figure out what it is. You get a 3 when you plug in negative 1. You get a 0 when you plug in 2. You get a 0 when you plug in 0. And you get 1.034 when you plug in 4/5. So what is our max and what is our min? Well, this would be our absolute max, and these would be my absolute min. So absolute max at x equaling negative 1. And we have absolute mins at x equaling 0 and 2. So this would be my entire conclusion for that problem. All right, very good. Hopefully you don't have any questions. If we do have questions, obviously that would be a case where you want to make sure that you contact me at any time. All right, and looking into our last piece here for derivatives and what they yield from us on our graphs. And so, first derivative is related to the slopes of the tangent. It gives us increasing, decreasing. It gives us a local max and a local min. The second derivative of a function is actually also going to have some geometric meaning as well. So this is just a curve of the sine curve. And what I want you to identify here are some places that are like the tangents, okay? So if I look here and I try to get the slopes of all these tangent lines, notice that I have numbers that would actually be values that are, I'm just kind of working here. Maybe this is a slope of negative 1. This is a slope of negative 1/2. This is a slope of 0. This is a slope of 1/2, and this is a slope of 1. So if I try to kind of look at each one of those, I'm just guesstimating some slopes. What's happening as I get along the x-axis? As I go along there, those slopes are increasing. So here, f prime increases. So the slopes of the tangents basically increase. F prime increases the slopes, which means that the slopes increase as x increases. Okay? Now, what happens on these slopes here? If I try like this one, and I try like this one, and this one, and this one, and this one, say that our slopes here are, say 1, 1/2, 0, -1/2, and -1. Well, if we look at this situation, our slopes are now decreasing. So here, f prime decreases, which means that the slopes decrease as x increases. Okay? So, this is an idea of what we refer to as concavity. Okay? And this is the mathematical part of it, but I always like to do simplicity. Okay? Concavity basically is kind of the shape of your graph. Concavity, in this case, where our slopes are increasing as x increases, this is creating a concave up situation, what we refer to as concave up. I always think of it as like an x squared, like that part right there from here to here looks like an x squared. A positive x squared would be one that warrants concave up. And along this side over here, where I end up having the slopes that are decreasing, but in a sense, this almost looks like a negative x squared, and this warrants what we refer to as concave down. And this is the geometric piece that is added on with the second derivative. Kind of gives you kind of the look of the graph. Is it pointing kind of up, or is it opening down in a sense for concavity? Is what we relate that at. So let's do a definition here that let f be differentiable on an open interval I. F prime is increasing on I, then f is concave up on the interval. That's what we just talked about here. But if f prime is decreasing, all the slopes of those are going down on I, then f is concave down on that interval I. Now, there's a point at which things switch over, and on our graph, this is the point at which things switch over. That is actually called a very important point, and that is what we refer to as an inflection point. So if f is continuous on C and f changes concavity at some point, C, in this case we go from concave up to concave down, then f has an inflection point. At C. Okay? So, another property of concave up is that all those slopes of those tangent lines, those lines are underneath the graph. Concave down, all the slopes are, or the tangent lines are above the graph when you're looking at it from left to right. Okay, so what is our test for concavity? I said it is yielding the second derivative. Well, if our derivative is increasing and our derivative is decreasing, that means in order to get the increasing and decreasing of the first derivative, we have to assess the second derivative. So here's our test for concavity. Suppose that f double prime exists on an open interval I, then if f double prime is greater than 0, then f is concave up on I. So if f is increasing, the derivative assesses the increasing and decreasing of this function, then that means that f double prime has to be positive if we are increasing, and f double prime has to be negative if we are concave down on some interval. Now, again, if f double prime changes sign over C, then C is what we refer to as an inflection point of our function. Okay? And so those things are very, very important. The point in there. When we are assessing, analyzing graphs and such. Okay? So let's look on the next page as some examples of this concavity. So you can see some of these. This is be a concave down. If I kind of were to extend that, that kind of gives me the downward shape. Concave up gives me kind of that upward shape. Sometimes you have to kind of cut them off. This, because it does go from down to up, is an inflection point at f equaling 0. Here, this would be a case where our derivative, or our second derivative is equal to 0, but also it almost looks like our first derivative would equal 0 there as well. Here we have a completely concave up function where our second derivative is equal to 0, but it is not an inflection point because our concavity doesn't change. So you'll get that as a c value, but you have to assess that sign change over c to definitely include if it is an inflection point or not. Here we go from concave up to concave down. We have an inflection point there because it does change over concavity, and it does say there that our f double prime does not exist. And here's a situation here where I end up having one of those cusps or whatnot. Then it is concave down on the left of C and concave down on the right of C. Therefore, C is not an inflection point here. It has to have a sign change, okay? So this would be that f double prime here is negative, then it's a positive. Here, these would be plus and plus over the C. This would be a plus and then a minus for concave up and concave down, and this would be a minus and a minus. So again, the only time that we have an inflection point is over a sign change in the second derivative. Okay? So let's use these conditions to sketch a function that has these qualities where f prime is positive and f double prime is positive as well. So if I have f prime to be completely positive and f double prime to be completely positive as well, what does the first derivative tell us? It tells us increasing, decreasing. It gives us max and mins. Here, since it's always positive, that means that we are forever increasing for this function. But for our second derivative, which determines concavity, we're always positive, so a positive yields a concave up. So we are concave up always for this function. So we need an increasing function always that is always concave up. So if I'm always increasing, that means I'm going to keep going up and up and up. So if I want to have it concave up, something like this would satisfy the conditions that we have. Okay? Again, I like to do these little line charts just so that you have things intact. One for the first derivative and one for the second derivative. So here, notice that we are on an interval from 0 to, or negative infinity to 0 and 0 to infinity. So I'm going to break it there by 0. So let's go for the left side of 0. We know that our first derivative is negative. It's less than 0. And our second derivative is positive. So it is greater than 0. Here, we also have a first derivative that is positive and a second derivative that is positive as well. So what do we know about 0 on our first derivative? This tells me that I'm decreasing. This tells me that I'm increasing. And if I'm decreasing then increasing, that means that I have a minimum right here at 0. That's what that's telling me. Here, if I have a second derivative, that means I'm concave up. I'm concave up, and this is not an inflection point. So that means I'm continuously concave up for this entire function. So what would a sketch of that be? Around 0, that's where my minimum occurs. If I am decreasing from the left of 0 and concave up, I have to have something that looks like this. But then if I'm increasing then concave up, I end up having to do something like that. So it seems like a parabola is one that would satisfy these conditions, and it does. I'm concave up always, and I'm decreasing then increasing with a local minimum at 0. Okay? So there's lots of graphs that you could have on that. There's not one graph that's going to satisfy all of those, so there could be multiple answers for that. Now, determine the intervals on which the functions are concave up or down and identify any inflection points. So if we're looking for concavity, we're looking for the second derivative, and we're looking for a sign change to be able to identify any inflection points. So what do we get for our first derivative here? First derivative gives me a negative 4x cubed minus a 6x squared plus a 24x. If I do the power rule, I don't care about anything here. They're not asking me increasing, decreasing. They're just asking me concavity. So I'm going to go directly into finding the second derivative. So I'm going to bring the 3 out front and give me a negative 12x squared minus a 12x plus a 24. And this is where I want to know where it's equal to 0. Okay, to find those critical or possible candidate of inflection points. So I'm going to first divide everybody by a negative 12. And when I do that, I get x squared plus an x minus a 2 equals 0. And I can factor that quadratic. So there's two possibilities here. Let's go x plus 2 and an x minus 1, which yields on my graph of f double prime, that yields what makes that 0 is negative 2. What makes that 0 is positive 1. And so here, this is where I need to check f double prime. What do each of these yield out whenever I throw a value in? Now again, you can use this guy right here, or you can use this, or you can use this. Notice that I don't have any double roots, so that means that each of these are going to have to alternate. I'm going to choose 0, because I like to choose 0. That makes this positive, that makes this one negative when I throw 0 in, and a positive times a negative is a negative. I don't care what the number is, I just want to know what the sign is. So because there are no double roots, that means this has to be a plus and that has to be a plus. If you don't believe me, pick out a number from each one of those regions, plug it in, and you'll prove to yourself that those have to be pluses. So what do we know about the concavity? When is it concave down and when is it concave up? Well, concave up means that we're positive. Concave down means that we're negative. And are there any inflection points? Absolutely. I have two different sign changes here, so I do have inflection points at negative 2 and 1. So concave up will be from negative infinity to negative 2, and from 1 to infinity. Concave down is going to be from negative 2 to 1, and I have inflection points at negative 2 and 1. So that is the conclusion of that problem. Okay? All right, very good. Let's try the next one, which is a rational function. So the derivative, second derivative may not be so pretty, but we'll see how it works, okay? First off, note that the domain here is going to be all t that is not equal to negative 2, so we can't choose negative 2, and negative 2 can't be any of our points here, okay? So, but it is one that we have to check over because it could be a place where we're undefined, okay? So, g prime at 2, or g prime of t, excuse me, doing a little quotient rule here, doing a little ho-de-hi, so t plus 2 times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 1, all over t plus 2 quantity squared. Now, if I simplify this a little bit, on the top I get t plus 2 plus t minus 1. Whoops, sorry, minus, I did that backwards, sorry. Let's undo that. T plus 2 minus t plus 1. Excuse me, that way those t's cancel out, and I still wrote, yes, a plus 1. Okay, so that ends up giving me a 3 all over a t plus 2 quantity squared. Okay? So now, I need to take the derivative of that. But I'm going to make life a little bit easier on myself and rewrite this as a negative exponent. So I get 3 times t plus 2 to the minus 2. And that's going to help me out when I have to take the derivative on the next piece. So g double prime of t, I'm going to use a power rule with the chain rule. So I'm going to bring the negative 2 out front, gives me a negative 6. Decrease this power by 1. Remember, when you subtract 1, it becomes a minus 3. Take the derivative of the inside is just a 1, so I'm not going to choose to write that because it doesn't change anything. So therefore, my derivative is this. All right, now, here we have to determine critical points or the possible candidates, and it's where it's equal to 0 or where it's undefined. So, undefined, whoops, so I need a 2 there. It's going to be undefined at the value in our domain where we're not allowed to be, which is at negative 2, but it doesn't mean that you can't have change in concavity there. I like to, if it's undefined at negative 2, kind of put a little dash part there so I know. Now, what happens if I throw in a number that is left of negative 2 into the second derivative? Remember, this is evaluating g double prime. say -3. -3 plus 2 is a -1, cubed is a negative. Divide that into a negative, becomes a positive. And then, when I choose, say, 0, if I put 0 in here, I get positive down below, negative on top. When I divide, I get a negative. So, here, -2 is not an inflection point because it's not in my domain. But I do have concavity differences. So if I'm going to go concave up, that goes from -infinity to -2. And concave down, we are going to go from -2 to infinity because that's where it is negative. And there are no inflection points because -2 is not in my domain. Okay? All right. Very, very, very good. Finally, we get to our last little test in this section, which is what we refer to as the second derivative test. And we can determine max and mins from the second derivative test, okay? So, basically, what do we know? Okay, suppose that f double prime is continuous on an open interval containing c with f prime of c equaling 0. So there's a possibility here that we do have a local extrema, okay, and it is defined. It's not one of those that does not exist where it can possibly be there. Now, if f double prime at c is greater than 0, the derivative is positive. That means that I have a concave up. Then we can say that f has a minimum at c. If my second derivative at c is less than 0, that means we have concave down. So it's almost kind of backwards. Then f has a local maximum. When I have a situation where I'm a concave down, we would end up being something like this, where the chance of having that maximum at c. If f double prime at c equals 0, then the test is inconclusive. F may have a local max, a local min, or neither at c. Okay, so I'm just doing one example here with you on that in this parabola, or I'm sorry, in this polynomial. That parabola is a polynomial, it's a cubic. And so we want to locate the critical points of our function, which is where f prime equals 0, then use that in the second derivative test to determine whether we have corresponding maxes or mins. Okay, so let's first find our critical values. Bring the 3 out front, we get 3x squared. Bring the 2 out, cancels this 2, leaves me with a 3x minus a 36. I'm going to figure out when that's equal to 0. I'm going to divide everybody by a 3 and get x squared minus x minus 12 equals 0, and I can factor to get my critical points. So let's go x minus 4 and an x plus 3. The roots that I have for each one of those is 4 and -3. And those are my possible critical values that I could have maxes and mins. So, critical points are at -3 and 4. What I now need to determine is what is f double prime at -3 and what is f double prime at 4. In order to determine is this a max or is that a min. So it's just another way to figure that out. Now, I'm going to go ahead and take the second derivative of this guy right here. Now, don't do it where you're divided by 0. Do the second derivative up here. So, f double prime of x is going to be a 6x minus 3. And that's what I now need to plug in, -3 and 4. So if I put -3 in there times 6 is -18 minus 3 is a -21. If I put 4 in there, 4 times 6 is 24 minus 3 is a positive 21. I think that might just be a coincidence because that doesn't always happen. So what do I know? The second derivative is negative. That means I have concave down at that point. So therefore, we have a maximum at x equaling -3. And here, because this is positive, we have a concave up situation because our second derivative is positive. Concave up means that I have a minimum at x equaling 4. Okay, so that would be what we can conclude using the second derivative test for local extrema. Okay, now we are finished doing problems, but what I wanted to give you on the last page of your notes is a nice little, if it'll go to it, nice little conclusion or summary of what we know from different pieces out of this section, because this section is really big, okay? F is differentiable on an interval, then it has a smooth curve. If our first derivative is positive on an open interval, then we are increasing. If our first derivative is negative, then we are decreasing. What happens if I change signs from a first derivative being increasing then decreasing? That means I have a local max. Decreasing then increasing, I have a local min. Same way here, increasing, decreasing, first derivative equals 0, and our second derivative is less than 0. That's the second derivative test. First derivative equals 0, and second derivative is positive, means I have concave up, means I have a local min. So these are kind of the second derivative test one. If my second derivative is positive, that means we are concave up, so it looks something like that or like that. If our second derivative is negative, we are concave down. And if we change that concavity where f prime changes from a plus to a minus or vice versa, a minus to a plus, then we do have an inflection point. So I wanted to give that to you. It's in your book. And so it's a nice way to summarize everything up. So we've gotten basically through all this analytic stuff of graphing. So now you have all the tools to be able to sketch some graphs given given all this little piece of information. So that's what we're going to do in the next section, is kind of pull all this together. Give a function, can you do a nice graph of that? And so all of these tools from section 1 and section 3 are going to be really, really important in section 4. So until next time.